Now that we've got the basics down, let's see what happens when things go wrong. We're going to open up our first case file, alpha thalassemia. And as you can probably guess from the name, this one is all about those alpha globin chains. It's a story that really revolves around the number 4.
The crucial word here is deletion. With alpha thalassemia, the problem isn't some typo in the genetic code. No, it's that entire genes, the actual instructions for making alpha globin, are just gone. They're completely missing. We all have 4 copies of this gene, and the disease is defined by how many of those 4 have disappeared.
And this slide really shows the consequences perfectly. This is not some all-or-nothing condition. It's a spectrum, a sliding scale of severity that lines up directly with how many genes are missing. As you can see, the more pieces of that blueprint that are lost, the more severe the outcome gets.
So let's break this down. Let's take a closer look at this spectrum, going from just 1 missing gene all the way to 4.
Okay, so if you're missing just 1 gene, you're what's called a silent carrier. No symptoms, you'd probably never even know. If 2 genes are deleted, that's called alpha thalassemia trait. You might have a mild microcytic anemia, which really just means your red blood cells are a little smaller than usual, but you're generally healthy. But when 3 genes are missing, everything changes. This is hemoglobin H disease, and it causes severe anemia with chronic hemolysis, meaning your red blood cells are destroyed faster than your body can make them. And finally, if all 4 alpha genes are deleted, well, that condition is called hydrops fetalis, and it's incompatible with life.
Okay, let's close that case file. Now it's time to open our second one, beta thalassemia. Here, we're shifting gears from the alpha chains to the beta chains, and from a story of 4 genes to a story of just 2. 2. That's the number to remember here. We are all born with 2 genes that hold the instructions for making beta globin, getting one from each of our parents.
Now here is the single biggest difference, so listen up. Beta thalassemia is not caused by gene deletion. The genes are there, but they have mutations. Think of it like a critical typo in the blueprint. These mutations either just reduce the production of beta chains, that's called beta plus, or they stop the production entirely, and we call that beta 0.
And this all leads to 2 main outcomes. If one of your 2 beta genes has a mutation, you have what's called beta thalassemia minor, which is generally pretty mild. But if both genes are mutated, the result is beta thalassemia major, and that's a life-changing diagnosis. Without any functioning beta globin genes, severe anemia develops within the first year of life, and survival depends entirely on lifelong blood transfusion.
We're going to follow the evidence, just like a doctor would, moving from one clue to the next to narrow down all the possibilities and crack the case.
You know, our whole journey starts with a really basic question. A patient might come in feeling tired or weak, but how does a doctor officially confirm they have anemia? Well, it all comes down to the numbers.
Now this flowchart, this is our guide. I know it looks incredibly complex at first glance, and that's because it is. This is the master map doctors use to navigate all the different types of anemia. But don't you worry, we're just going to follow one specific trail together.
Okay, so here's the crucial point. Anemia isn't just a feeling, it's a measurable condition. The investigation doesn't truly begin until a blood test confirms that a patient's hematocrit or hemoglobin levels have dropped below these very specific thresholds.
So once anemia is confirmed, the investigation takes a sharp turn. The next step isn't about the cause just yet. Nope. It's about looking at a really critical characteristic of the red blood cells themselves. It's a clue that splits the whole path into 3.
And that clue? It comes from something called the mean corpuscular volume, or MCV for short. This is a super powerful measurement that tells us the average size of a patient's red blood cells, and that one number immediately helps us narrow down the possible causes.
Think of this single value as a major fork in the road. Are the cells too small, normal-sized, or too big? Each path leads to a totally different group of suspects. For this explainer, we're heading down that first trail, the microcytic path, where the red blood cells are smaller than they ought to be.
All right, let's head down the microcytic trail and see how this clue helps us build toward a specific diagnosis. We know the red blood cells are too small, but what could possibly be causing that?
Just by confirming those small cells, we've narrowed our list of suspects down to these 4 main possibilities. That's a huge step forward. But now, we gotta figure out which one of these is our real culprit.
So how do we do that? How do we pinpoint the exact cause when the cells are small in all 4 of these conditions? We need another clue, right? A deeper dive into the blood to tell them apart. And luckily, the next set of tests gives us that answer. Okay, now this is where it gets really interesting. These detailed iron studies create a unique fingerprint for each condition. Just look at the patterns. In iron deficiency, the body's iron stores, called ferritin, are low. So the body ramps up production of transport proteins to grab any iron it can find. That's the high TIBC. But in thalassemia, the pattern is the opposite. Iron and ferritin levels are actually high because the body isn't using the iron it already has.